Hi guys, this is Val from Core Conservation. Beautiful day today. We're in Newcastle. This is a late Victorian building around the turn of the century, and it had some problems. This is one of the living rooms. As you can see, some work has been undertaken here recently, and the wall has been replastered about 2 months ago. There was rising damp, or these rising damp inside the building, and I'm going to show you a few bits outside in a moment. And 2 months later, after it has been replastered with a sand and cement and gypsum finish, salts came through. And these are some white puffy stuff, which are quite common in all buildings. Holding the light so you can see it. Here's the socket. And everything, just the soles just keep falling and they keep crumbling, and we can see them everywhere. And 2 months following the replastering, the soles came through again. And now the owner of the building was looking for a long-term solution to the problem. This is the other corner of the room. Another replastered area, we can see the white soles coming through at quite high, about a meter from the ground, over a meter and a half from the ground. The surface again looks crystalline. It looks like puffy snow, quite nicely shining actually. We can see some damp marks here, the gypsum discoloring, getting this dark color. Everything is crumbling, and also this whole wall is quite visible that it has been replastered a couple of months ago, and the soles have been already brushed off. The lower part of the wall is dampened, as we can see from the color, and you can see the soles basically on the skirting board everywhere, and on the carpet as well. Some of the problems are also creeping up in the other part of the living room. We can see here around the sockets, the soles crystallizing, or near the base of the wall. But they are also equally present in the dining room area. This is the old external wall. Looking at the wall's thickness, now for the past 3-4 decades has been internal, and we can see the sole crystallization occurring on this wall as well, ongoing on this wall as well. This is another internal wall in the dining area. Looking at the soles, and also starts creeping up here above the skirting board in the old section of the building. So it's all over the place. This particular building had a lot of its features preserved during the past century or decades. You can see the ceiling is still to a large extent original. The tall skirting boards are also quite old, kind of typical to the Victorian era. And some of the internal decorations have been really well preserved. The floor is a traditional Victorian construction, timber floor. It's about a foot, half a meter above the outside level. And then we have these really tall skirting boards preserved nicely. So the wall is easily over half a meter above, the base of the wall is over half a meter above the ground level outside. Moving outside, we can see that the base of the walls are a bit poor condition. We can see the stone being affected in comparison to the upper part, which is all even. You can see it here as well, the stone near the lower part of the wall. To determine the moisture content of the walls, I have taken some samples from various parts of the building. Here is one of it, about a foot from the floor, or maybe about 2 feet from the outside ground level. I just wanted to highlight a few things. First of all, the deeper I went, basically the darker the color of the sample became. We can see on the top here, kind of in the center of the video, it's kind of a lighter color because I was pulling it out and was actually bringing out some of the stuff from closer to the surface. However, this bit here on the left and the right, here we can see the darker color, so basically the wall was damper inside that on the surface. The other point which I wanted to make, if you look here carefully, we can see that the sample, let me see if I can zoom in here, we can see that the sample is actually creates like lumps here, like almost like little sausages, because and this just shows here is a bit more powdery, and here it actually more kind of lumps together because basically this is because of the humidity. So the sample basically on the side here is actually significantly damper. It almost creates like a bit of muddy type of thing rather than being porous. And here we can see on the side as well, we can see that the sample inside the wall is basically kind of lumping together. Based on my experience, this probably is going to be around 10% or higher, because when it starts lumping together, then it's anyway above 88% moisture content. It's quite significant. And again, this is an internal wall, not rainwater ingress. I'm about 1.5 meters from the corner of the building, and on the other side we just have, this is actually an internal wall. So let's put it in the analyzer and check it out. I zero it, and I'm trying to scoop in the internals of this. So I'm trying to take 2 grams of sample from here. Well, it is what it is. I just put the whole lot kind of there, 2.93 grams, okay. So that's the sample here. Close it off. So it's stable. We start at 3 grams, 0.0%. And then, yeah, and you can see that the weight of the sample is decreasing, which is basically shown here. 2.9 and is decreasing. The moisture content is increasing. Here also have the time, 18, 19, 20 seconds. Now the machine is basically warming up. It should reach 105 degrees operating temperature. This should actually take about 30 seconds to get there. So yeah, and once it reaches the temperature, it will stop. And yeah, here we have so far 3.5% moisture content, and the weight of the sample is decreasing because the water is evaporating on the top of the machine. So yeah, let's just leave it here for a few minutes and see what we get. It's already at 91, 93 degrees, so it's getting there, and the moisture content is nearly 5%. Just to jump in quickly, the moisture analyzer reached its operating temperature, 105, as shown here. So that's the target temperature, that's the operating temperature. We are about 6.5% moisture content, and obviously the sample is losing weight. So here we are, we just finished the measurement. Here's the original sample, now it's lighter. And it took about 4 minutes and 19 seconds, and the moisture content of the sample is 8.85%, and that's what we have basically. We started at 3 grams, and then it went down to 2.74, losing almost 10%. So it's 8.85, almost 9% moisture content, which again for a brick is about 3 times more than what's considered dry. Okay, so we have taken a moisture reading here, and this was around 9%, 8.95, and I'm going to take another reading from higher just to see the moisture profile. Okay, so we are done. And the moisture, this sample is 9.46%, slightly higher at the bottom than at the bottom, which can happen because of the additional hygroscopic effect of salts. We're going to check that in a moment as well. Just some quick comments about what we have here. So we have multiple variables. Obviously we have the old wall fabric, which is over 100 years old, around 120, 30 years old. This is an internal wall, so it's not subject to any rainwater or gutter or other type of problems. Then we have the modern plaster here, which basically for the past 2 months, I know it's a cement plaster and the gypsum finish. What was before that, chances are it was another modern plaster. Also slim chances, but it's a possibility that it was the original lime plaster. I don't know. Let's assume anyway at the moment we have the old plaster. And then we have the crystallizing salts on the surface. Now, very, very easily one can come to the conclusion that yes, the building has a modern plaster, that's the cause of the problem, they made a mistake, and the plaster is actually driving the humidity up the walls, take the plaster off and that will solve the problem. Yes, it's a fair point, but there's more to this. Also outside the building, the bricks are really nice, but is also cement pointing. So obviously someone could point it out that yes, the cement pointing needs to be raked out, lime pointing should be added, and that will also solve the problem. That's the cause of the problem, but there's more to it, unfortunately. So what we have here, yes, these issues can be factors which contribute to the problem. However, let's think about this. Cement plaster is non-breathable, but the only time when it can cause problems when it is an underlying problem. If there would be no moisture ingress coming, no rising them coming from the ground, so would be no moisture source, and the wall would be completely dry because nothing is keeping it wet, then obviously the cement plaster would not cause an issue like it doesn't cause issues in modern buildings. Why the talk about all these breathability in old buildings and nobody really cares about what's with the new buildings? Because new buildings, they have a damp-proof course, everything is nice and dry. As a result, moisture doesn't come up and nothing to accumulate. So obviously if there's no moisture accumulation occurring as an underlying problem inside the building fabric, then cement could not do any harm. Cement only can trap the moisture where it exists. If there's no moisture in existence, nothing can be trapped. So we have the moisture rising from the ground, and this is not necessarily to capillary action. I will leave a link behind the video about the mechanism of rising damp as the latest research has shown. So the water is coming up and is bringing up salts. Now the problem of the salts is that they accumulate in the wall fabric, and they tend to accumulate in the higher parts of the wall, or anyway, not necessarily the lower part where they are actually in diluted form. And as a result, the moisture basically can be caused in the center part of the higher part of the wall by the rising damp and also by the salts, which can absorb humidity from the ground, from the environment. So we have two moisture sources from inside the wall or from the ground, and also the hygroscopic effect of salts. That's why it can happen that, as we saw it, that the lower point was 8.95%, 9%, and this was slightly above 9%, and the third point now is basically being determined as we speak. And the moisture content of this sample is 2.83%. So it is a possibility that moisture basically is not necessarily decaying. Overall it is decaying, but there are other areas where is high salinity. Then we have other areas which basically can be damper than lower areas in certain cases. So that's what we have, and then obviously the moisture which is coming out and some of the salts which are absorbed from the ground, they can react with the salts in the gypsum and in the modern building fabric and with the additives and everything else, and creating some really spectacular salt crystallization problems. So overall, it's quite simple. Yes, ideally one should actually deal with breathable materials, with lime, but cement and modern materials only trap the moisture when there's something to trap. So when there's moisture accumulation behind, one has to think about it, what the heck is causing it. And the many causes can be present externally and internally. In this case, because it's an internal wall, the source of the moisture is the ground. And by taking several readings, one can determine and can prove quite easily basically that the rising nature of the moisture in a sheltered environment. So how are we going to solve this issue? Well, the first point is actually to deal with the rising damp, which is basically keeps piling up the salts in the wall fabric. In this particular case, we have done that with a magnetic damp-proof course. This is a new non-invasive technology, sits on the ceiling, looks like a lampshade or a beehive, and basically deals with the moisture remotely. I leave a link in the description so you can actually read basically the working principle and what it does. It's quite interesting and it works. The second part of the solution is obviously now dealing with the plaster, because the plaster is blown and it has all these salts. The solution is unfortunately not just the lime, because what happens if you hack this plaster off and you add lime to it or apply lime, the salts are going to migrate into the fresh lime, and chances are that the lime is going to start blowing in a few years, which probably many of you have witnessed. In order to solve the problem, there's a particular technology here. Basically, the plaster needs to be hacked off, and then a salt-resistant lime base coat needs to be added. We use the MGN base coat because this is basically the best on the market. It's used in Venice, is originating from Rome and kind of the Roman heritage, and it basically does two things: it blocks the salts and also can stop liquid water. So applying this particular base coat first on the bare wall, it will help overcome this problem. Here in this footage it's applied on a different building, but you can see the concept. Basically it's applied first, and then you can apply the lime on top of that. This way your lime plaster is basically protected by this volcanic salt filter, open pore salt filter, because it's a lime plaster which breathes, and it will actually prevent it from blowing. As we can see here, the salts have blown the plaster. They came through the cement and the gypsum plaster. This can be all prevented, and then as a result the decoration is going to stay nice and clean, salt free. It's not going to blow for a very, very long time. How long? Decades, basically 30, 40, 50 years easily. Hope you found it interesting. If you have any questions, feel free to leave it in the comments, and see you in the next video.